Dear students, let us look on to this problem. A continuous beam ABC is supported on the column BD as shown in the figure. So you consider ABC as a beam member which is supported on a column BD. So we are going to analyze this framed structure. So the span and the respective moment of inertia should be noted, and the loading, it is a point load, and here it is a UDA. So what is the procedure? So to find fixed end moment values, so M bar AB, so a point load with varying spans, distances, so minus 10 into 2 into 3 square by 5 square. Second one, M bar BA, minus 10 plus 10 into 3 into 2 square by 5 square. Next one, M bar BC, minus 2 into 3 square by 12, and M bar CB plus 2 into 3 square by 12, and MBD as well as M bar dB, which is equal to 0 because there is no load in the particular span. So let us calculate these values as 7.2 kilonewton meter, here 4.8 kilonewton meter, minus 1.5 kilonewton meter, plus 1.5 kilonewton meter. Next one, distribution factor, second step. Distribution factor, we can form a table because here the joint B consists of 3 members. First of all, joint member and the relative stiffness K and summation of stiffness values and distribution factor. So I have written very shortly. Only one joint to be considered. 3 members are connected in the joint. So first of all, joint B. The members from joint B is BA, BC and BD. So the K value for BA, where the far end is fixed, is I by L. So I is 2 times of I divided by L is 5. From B to C, far end is simply supported. So 3/4 of I by L. So 3/4 into I by 3. BD, the far end is fixed. So I by L. I by L is 3 meter. 3 meter. So the summation of K is 2I by 5 plus I by 4 plus I by 3, which leads to 59I by 60. And the individual distribution factor, the relative stiffness divided by summation of stiffness values 2I by 5 into 60 by 59I, which is equal to 0.41. For the second number, I by 4 divided by 60 by 59I, which is equal to 0.25. Next one, I by 3, actually it is multiplication, into 60 by 59I, which is equal to 0.34. So the distribution factor is 0.41, 0.25 and 0.34. And next step, for our comfortness, we can calculate the free bending moment values. While you plotting the bending moment diagram, it is necessary to superimpose the free bending moment diagram. So for the span AB, MAB, we can name it as FMAB equal to WL by 8. So 10 into 5 by 8. Okay, okay. It is varying in length WAB by L. So 10 into 2, 3 divided by the span is 5. That is WAB by WAB by L. Because it is not central point load, WAB by L. So which is 12 kilonewton meter. For the next span, MDC is WL square by 8, maximum moment, 2 into 3 square by 8, which is 2.25 kilonewton. So with the available values, we can go to the moment distribution table. So moment distribution table comprising of joint and member and distribution factor and fixed end moment. So the joint, first joint is A, the second joint needs some spacing to accommodate three members, and the next joint C, and finally D. So we can draw the separators. I'm going to give more space for the joint B. So it is only for our next one member. Distribution factor also you can draw a line. Okay. Next one, the member identification AB for the joint B, BA, BC, BD is there. So I am going to separate these three columns. Okay. And CD at the joint C and DD at the joint D. The distribution factor for BA is 0.41. Here it is 0.25. BD it is 0.34. The fixed end moment value AB minus 7.2, BA 4.8, and BC minus 1.5. BD there is no load, so it is 0, and the CB is plus 1.5. So you have to take more care while writing the fixed end moment value. You check for the correctness. DB also there is no load, so it is 0. So first of all, I'm going to roughly draw our section. So this is our number. So these are the fixed support. Here it is simply supported condition. Okay. So the simply supported condition, the bending moment is 0. Fixed condition, there will be some moment. So at A, it is meaningful that minus 7.2 can be present at A. But at C, the 1.5 should not present here. We have to release the moment to become 0. So first thing is we are going to balance the support C because it is a simply supported condition. So if you apply minus 1.5, 1.5 minus 1.5 will become 0. Okay. Then look over the support C. C is connected to the nearest B. So the half of the moment can be carried over to the intermediate support, which is considered to be rigid. So the C to B should be carried over. The CB and BC is relatively connected. So the minus 1.5 should be halfly distributed here as minus 0.75. You should not carry over from C to the nearest span BD. It is relatively meaningful to carry over C to B. So you search for the term BC. So minus 1.5 by 2 minus 0.75 should be carried over here. So you draw a line. So our initial procedure is to balance any simply supported condition present in the problem. Then only we can start our ordinary procedure. Okay, now we just add minus 7.2, 4.8, minus 2.25, and still it is 0, and simply supported moment becomes 0, and this span also with the 0 moment. So now you add these two, 4.8 minus 2.25, some unbalanced moment will be presented. So this step will be named as carryover. You can write here. So next one, by balancing the joint B, that for the summation of moment equal to 0, the unbalanced moment 4.8 minus 2.25 equal to 2.55 plus 2.55. While you applying minus 2.55, it will reach to the equilibrium condition. So this minus 2.55 should be multiplied with the corresponding distribution factors 0.41, and right here minus 1.05, minus 2.55 into 0.25 is minus 0.64, minus 2.55 into 0.34 minus 0.87. Now the carryover should be done. From the joint B, A should be carried over to half of the moment, and B should be carried over to half of the moment. You can easily carry over minus 1.05 from B to A. So it is minus 0.525. Next, B to D should be carried over, but the nearest span we have mentioned as CB. We should not carry over to the nearest span. It should be carried over to B to D. B to D. So minus 0.87 by 2 is minus 0.435, should be carried over to the D support. Okay. Then further balancing of over and carry over was done. So now, so this step you can write this carry over. You add this value minus 7.725, here 3.75, minus 2.89, minus 0.87, C to B is 0, here it is minus 0.435. And you check whether the summation of moment at joint B equal to 0. If you add 3.75 minus 2.89 minus 0.87, more or less it is equal to 0, or it will give some 0.01 variation. So we can eliminate this small variation, and we can finish the iteration process for this problem. So our moment values MAB minus 7.725, BA 3.75, BC minus 2.89, BD minus 0.87, CB simply supported moment 0, and DB minus 0.35. With this available value, we are going to draw the bending moment diagram. So you roughly draw the section and mark the direction. From A to B, it is anticlockwise of 7.725. From B to A, it is clockwise, which is 3.75. From B to C, it is anticlockwise, 2.89. And B to D, if you see through this, you can mention as anticlockwise of 0.87. From D to B, also anticlockwise, 0.435. So next you extend the ordinate on the tail side. So it is 7 point. I'm going to consider the minimum ordinate because you try to draw for a particular scale, rough scale, and here it is 3.75, and also at the same point we should note 2.89. Here the moment is 0, and here on this direction is the tail's direction, so minus 0.87. Here it is 0.435. So you connect the points. First 7.725 to 3.75. Sorry, 7.725 to 3.75, the topmost point. Next one 2.89 to 0th point. Next 0.87 to 0.435. Now you superimpose the free bending moment diagram. The first value is 12 kilonewton. Okay, is 12 kilonewton meter. Here it is 7.725. This value is 3.75. Next, the UDL value is 2.25. So consider some rough scale so that you can easily understand the magnitude or variation of bending moment at each span. So 2.25, 3.75, and 12 and 7.25. So this is the BMD for this problem.